Hello, students. Uh, Bodhee Prep has prepared topic tests for you. These topic tests are to be taken once you've completed the basic concept of the topic and you're ready to take a timed test. So, time yourself through these questions. With every test, there is a video which gives you the solution and a broad analysis of the test and the kind of questions that should be attempted, what would be a good attempt, and so on. And if you like the tests and find them useful, there are more than 200 topic tests available on the Bodhee Prep Android app. The link for the app is in the description of the video. Please download the app and make use of these tests. This specific video is about the topic remainders, and the test number for the topic is test 4. Overall, this test was, I think, moderate to high level of difficulty paper. About 5 to 6 questions net correct would actually be a good attempt. And again, the idea was some of the questions were pretty easy, some of the questions were very difficult. So identifying the difficult question and letting them go would actually be the challenge in this test. Attempt time, since we'd be attempting all questions, the time might go up to 25 minutes. If we do look at the questions, the first one says, suppose 3x leaves a remainder of 7 when divided by 16. What is the remainder when x is divided by 16? Suppose if I say x is a number of the form 16a plus b. So when x is divided by 16, the remainder is b. What will be 3x therefore? 3x will be 48a plus 3b. Now when we divide 3x by 16, the remainder we can see clearly 48a will be divisible by 16. The remainder will be 3b. This is given to us as 7. Obviously, b cannot be 3b cannot be 7, not a multiple of not a multiple or not an integer. 3b is not 7 because b will be 7 by 3 then. That means 3b has become a number which is greater than 16 and therefore a division happened. So since 3b cannot be 7, we can say 3b could be 7 plus 16, which is 23. Again, not possible because 3b plus 23, 3b being 23 will again not be an integral value for b. So 3b could also be 7 plus 16 plus 16. So basically, since we multiply b by 3, it becomes a number which is divisible by 16 two times over. This is 39. Now this is possible because 39 is a multiple of 3 and therefore we can say b is 13. So if initially the number was of the form 16a plus 13, dividing this by 16 will get a remainder as 13. 3 times this will give a remainder as 13 into 3, which is 39, which will get divided by 16 two times to give a remainder of 7. What is the remainder when x divided by 16? The answer becomes 13. Again, looks a very innocuous question or a very simple sort of a question, but I think easy to get confused with the numbers that you're getting. Therefore, I'd say moderate question. Attempt time should be about 2.5 minutes for this question. What is the remainder when 3 raised to power 391 divided by 91? Okay, looking at the power of 3, which is close to a multiple of 91, 9 8s are 8, 728. 729 is the power of 3. 729 is 3, 9, 27, 18, 243, 391. So 3 raised to power 6 is 729. 3, 9, 27, 81, 243, 729. 391 here is not divisible by 6, but 390 will be divisible by 6. So we write 3 raised to power 391 as 3 into 390. Take out 6 from here, 3 into 3 raised to power 6. Here we'll have 6, 6 are 36, that's 65. And therefore this can be written as 3 into 729 raised to power 65. Now if we divide this by 91, clearly we can see 91 when dividing 729 will leave a remainder of 1 because this is nothing but 3 into 728 plus 1. So from the second part, we get the remainder as 1. And from here, we'll get the remainder as 3. So the overall remainder will be 3 into 1 raised to power 65, which will be nothing but 3. So I think the answer here becomes 3, and this would be an easy question. Should be able to solve this in about 1.5 to 2 minutes. Find the remainder when 2 raised to power 20 is divided by 100. Now there can be two methods. One is we try to find the remainder. So we say This is the question. We divide the numerator and the denominator by 4. So this becomes 2. 4 is 2 square. Divide by 4. This will be 2 raised to power 2018. 100 by 4 will be 25. A multiple of 25 close to a power of 2 is 1024, which is 2 raised to power 10. So 2 raised to power 8 into 2 raised to power 2010 upon 25, which becomes 2 raised to power 8 is 256 into 2 raised to power 10 raised to power 201. Further, this becomes 256. This is 10, not 6. Into 1024 raised to power 201. 1024 raised to power 201. This further becomes 256 into 1025 minus 1 raised to power 201. Now we can clearly see from here 256 by 25, remainder is 6. 1025 minus 1, remainder is minus 1 raised to power 201. So the overall remainder will be minus 6. Since it is a negative remainder, add it to the divisor to get the positive remainder 19. 19 is the remainder in this case for this division. But this division happened when we divided the original by 4. So the original remainder will be 19 into 4, which will be 76. Or what we can do is we can just try to find the last two digits of 2000, 2 raised to power 2020. That will be easier in this case because this is nothing but 2 raised to power 10 into 202, which is 2 raised to power 10 into even, and 2 raised to power 10 into even always ends in 76. So if we divide this number which ends in 76 by 100, we'll get 76 as the answer. 2-digit cyclicity. That will be an easier attempt in this case, but again, overall, it's an easy question. The steps might be involved, but about 1.5 to 2 minutes should be good enough to get this question done. Find the remainder when 8 raised to power 321 is divided by 800. Now, 8 raised to power 321 can be written as 2 cube raised to power 321. This further can be written as 2 raised to power 963 divided by 800. What we do is we divide this by 8. That is, divide by 8 or 2 cube. 2 cube removed from 963 will be 2 raised to power 960. Divided by 8 will be 800. Now this is nothing but 2 raised to power 10 into 96, which is even. This will be 100, not 800. 2 raised to power 10 into even ends in is a number that ends in 76. 76 divided by 100, or the last two digits being 76, will leave a remainder of 76. So for this division, the remainder is 76. We got that when we divide the number by 8. So the original remainder will be 76 into 8, which becomes 8 6 are 48, 8 carry forward 4, 56, 608. Hence the answer 608. I'd say a moderate level of difficulty question. 2 minutes should be good enough to answer this question. What is the remainder when Googleplex? Googleplex 10 raised to power 10 raised to power 100. So this term Google is 10 raised to power 100, and Googleplex essentially is 10 raised to power Google. This is the representation of a very large number. So basically we have to see 10 raised to power 10 raised to power 100 divided by 23, remainder is to be found out. Now, if we look at 10 raised to power n divided by 23 using Euler quotient, we can say the Euler number for 23 would be, because 23 is a prime number, we can simply say it will be 22. And therefore, using Euler quotient, we can say 10 raised to power 22 divided by 23 will have a remainder 1. And therefore, what we want to do is, we want to express this power in the form 22k plus or 22a plus b. So when we write 10 raised to power 22a plus b divided by 23, we will know that 10 raised to power 22a will leave a remainder of 1 into 10 raised to power b upon 23 is what we'll have to calculate. So the first step is to break down the Google power into the form 22a plus b. So we look at 10 raised to power 100 and then now divided by 22 to find the remainder and the values of at least b if not a, because a is immaterial. So we write this as 2 raised to power 100 into 5 raised to power 100 divided by 22. So divide the fraction or the entire thing by 2. This will give us 2 raised to power 99 into 5 raised to power 100 divided by 11. 2 raised to power 99 can be written as 2 raised to power 5, 19 into 2 raised to power 4. 8, 16. So basically, the power of 2 that is close to 11, multiple of 11 is 2 raised to power 5, which is 32. To take out 2 raised to power 5 from here, we needed 95. So I'm writing 2 raised to power 4 first. 95 can be split in 2 raised to power 5 and raised to power 19. Multiple of 11 close to a power of 5 is 3124. Multiple of 11, which is 5, 25, 125, 600, 5 raised to power 5. So 5 taken out from 100 leaves 20. This becomes, writing it at the top, so here, 32 raised to power 19 into 16 into 3125 raised to power 20. 32 will leave a remainder of -1. 16 will leave a remainder of 5. 3125 will leave a remainder of 1. So the overall remainder is -5, which becomes 11 minus 5, or 6 becomes the remainder. Now, if 6 is the remainder, we can say that 100 raised to power 100 or 10 raised to power 100 here can be written as this part, 10 raised to power 100, 22a plus 6 upon 23. So this circle I have replaced by this. 10 raised to power 22a leaves a remainder of 1, and therefore the remainder here will be based on 10 raised to power 6. 10 raised to power 6 is, say, 1000 into 1000, 10 raised to power 3 into 10 raised to power 3. Multiple of 1000, or if we divide 1000 by 23, 4s are 92 minus 603, 80 minus 69, 11. The remainder here will be 11 into 11 by 23, which is 121 by 23. Multiple of 92, 115. At 23 into 5 will be 115. So the remainder from here will be a total of 6. Hence the answer becomes 6. I'd say a difficult question, multiple steps involved. Easily 3 minutes to solve the question. According to Sun Tzu, there are certain things whose number is unknown. When divided by 3, the remainder is n. Okay. Suppose we are talking about n divided by 3, the remainder is 2. N divided by 5, the remainder is 3. N divided by 7, the remainder is 2. The remainders are not constant, and the differences are also not constant. What is the sum of the two smallest positive nodes satisfy this condition? So what we can do is, we can start with the first condition. We write the numbers that being divided by 2, 3 leave a remainder of 2. The smallest number will be 2. Then we add 3 to it, 5. Then we add 3 to it, 8. And so on. We'll look for the smallest number which satisfies the second condition from these numbers. So I'm just adding 3, 2, 5, 8, 11, 14 and so on. All of these numbers when divided by 3 leave a remainder of 2. As we can see, 8 is the first number which also leaves a remainder of 3. So the smallest number satisfying the first two conditions is 8. Now start adding the LCM of 15 and 5 and 3 to 8. So 8, 5 and 3 LCM is 15, 23, 38 and so on. And then check for the third condition. As we can see, 23 is when divided by 7 leaves a remainder of 2. So the smallest number which satisfies all three conditions is 23. The next number will be 23 plus LCM of divisors 3, 5 and 7, which is 23. LCM of 3, 5 and 7 will be 105. And therefore the smallest number is 23. The second such number is 128. What is the sum of the two smallest such numbers? 128 plus 23, which is 151, becomes the answer. Again, you have to check for three questions, but luckily the divisors are simple. Sorry, the divisors are simple and the remainders are small. So again, moderate level of questions, 2.5 minutes should be good enough to do the question. 7 says if b and c are real numbers such that fx is equal to x raised to power 5 plus bx square plus 2x minus 1 is divisible by x minus 1. So using the remainder theorem, we can say put x plus 1 is equal to 0, x is equal to minus 1. Substitute minus 1 here. That is f of minus 1 should be 0 because it is divisible, which means minus 1 raised to power 5 plus b into minus 1 squared plus 2 into minus 1 minus c should be 0, which means minus 1 plus b minus 2 minus c should be 0, which means b minus c is equal to 3. This is equation number 1. Leaves a remainder of 12 and divided by x minus 2. Put x minus 2 is equal to 0, which means x is equal to 2. At this point, f of 2 should be remainder 12 using remainder theorem. So 2 raised to power 5 plus b into 2 raised to power 2 plus 2 into 2 minus c should be 0. So 32 plus 4b should be 12, not 0. Plus 4 minus c should be 12 minus 24. 4b minus c would be equal to minus 24. 32 plus 4, 36. 12 minus 13 minus 24. This is equation number 2. This was equation 1. Now if we subtract, say 1 or equation 2 from equation 1. So b minus 4b minus c plus c cancel is equal to 3 minus minus 24. 7. So minus 3b is equal to 27 or b is equal to minus 9. If b is minus 9 and we put the value here, minus 9 minus c is equal to 3. So c will come out to minus 9 minus 3, which is minus 12. And therefore the function fx becomes x raised to power 5, b is minus 9. So minus 9x square plus 2x minus c is minus 12. So x raised to power 5 minus 9x square plus 2x plus 12 is the function that we have. We have to find the remainder on x plus divided by x plus 2. So put x plus 2 as 0. X is equal to minus 2. So the remainder when this expression is divided by x plus 2 will simply be f of minus 2, which becomes minus 2 raised to power 5 minus 9 into minus 2 whole squared plus 2 into minus 2 plus 12, which is minus 32, 4, 9, minus 36, plus 36. P is negative, minus minus plus, plus minus minus. Minus 36, not a problem. Minus 4 plus 12. So this becomes 60 minus 68 minus 72 plus 12, which is minus 60 becomes the answer. The remainder is option B. Again, application of factor and remainder theorem. The concept is straightforward, but overall, because some calculation involved, I'm saying moderate question, 2-minute solving time. Positive integer n when divided by 4 and 7 gives the remainder 3 and 2 respectively. Which of the following is true for n? Now, a number when divided by 4 giving a remainder 3 could be of the form 3. 3 plus 4, 7. 7 plus 4, 11. 11 plus 4, 15. 15 plus 4, 19. 19 plus 4, 23, and so on. Checking these numbers for 7. Divide by 7, the remainder here will be 3. Divide by 7, the remainder here will be 0. Divide by 7, the remainder here will be 4. Here it would be 1. Here it would be 75. And here it would be 2. So these were the numbers which when divided by 4 leave a remainder 2. We check them for remainder with 7. 23 satisfies both conditions. The smallest number is 23. The next such number will be 23 plus LCM of 4 and 7, which is 28. So 23 plus 28, 51, and so on. The general form of the number will be 23 plus 28n, where n could be a whole number. Which of the following is true for n? N is odd? Yes, because this is odd, this is even. Odd plus even will always be odd. So this is definitely odd. C gives a remainder 3 when divided by 28. Not necessarily. If we divide 23 in itself by 28, the remainder will be 23, not 3. So this is definitely wrong. Both A and B, so we have to check for B. N cannot be a perfect square. Now, if you put 23 plus 28n, which is an odd number, to be a square of E. E is an odd number, so E square will also be odd. Therefore, 28n is equal to E square minus 23. Now, if there is the square of an odd number, for example, 1, 9, 25, 49, 81, and so on, all such numbers, when divided by 4, leave a remainder of 1. So, from here, we'll get a remainder of 1. Minus 23 means a remainder of minus 20, or when divided by 4, 23 will give a remainder of minus 3. So from here we'll get a remainder of minus 2 when divided by 4. But this side is divisible by 4, this is not. And therefore this cannot happen. Hence, 23 plus 28 cannot be a perfect square. So the answer becomes option D, that both A and B are correct. I would say this is a moderate level of difficulty question. Point B could be a little difficult to prove, and therefore attempt time could be 2 to 2.5 minutes. The number n is represented by the base q numeral 1441. So n essentially is 1441 to the base q. When divided by 11, n is a remainder of 1. So the value of n can be written as 1 plus 4 into q plus 4 into q square plus 1 into q cube. So basically n in decimal form, the value will be qq plus 4q square plus 4q plus 1. This when divided by 11 leaves a remainder of 1. So n divided by 11 leaves a remainder of 1. So like we can say that n minus 1 is divisible by 11, which means q cube plus 4q square plus 4q. This should be divisible by 11. Clearly q is not 11 because we want a value of q which lies from 1 to 10, or from 2 to 10 basically. So we can say if we take q common, q square plus 4q square plus q square plus 4q plus 4. This should be divisible by 11 because q is not. Q square plus 4q plus 4 is simply q plus 2 whole square. Q plus 2 whole square should be divisible by 11. That will only happen when q plus 2 is divisible by 11. And the maximum value that q plus 2 can take is 11. So q plus 2 is equal to 11 or q is equal to 9. Because q could be a maximum of 10, the only possibility for q plus 2 to be a multiple of 11 was when q is 9. And that becomes our answer. Option D. I'll call it a difficult question because there is a concept of base involved, and the fact that q plus 2 square will give us the answer might be a little difficult to strike. 2.5 minutes to solve the question. 2 to 2.5 minutes to solve the question. 12 consecutive integers are added together. What is the remainder when the sum is divided by 4? 12 consecutive integers are added. Suppose the first integer is a, the second will be a plus 1, and so on. 12 will be a plus 11. This is a arithmetic progression. So the sum will be n number of elements, n upon 2 into first plus last element. This will be, we know that n is 12. Number of elements is 12. This will be 6 into 2a plus 11. Now, if we divide the sum by 4, sum is s. If we find s by 4 will be 6 into 2a plus 11 by 2 by 4. So dividing by 2, we get 3 into 2a plus 11 by 2. Clearly, the numerator is odd. 3 is odd, 2a plus 11 will be odd, even plus odd. Odd divided by 2 will give us a remainder of 1. But we reach this when we divided the numerator and the denominator by 2. the original remainder will be 1 into 2, which is 2. Hence, what is the remainder when the sum of is divided by 4? It will always be 2. I think moderate level of question, small chances of errors happening, and therefore I am saying moderate. Attempt time should be around 2 minutes. So if we look at the overall level of the test, the test was towards the difficult level paper or an exam. A good attempt would be 5 to 6 net correct questions, and the questions that I would want to select for myself would be 2, 3, 4, 7, 8, 10. Which are these ones? I think this was a question that might not work out in the exam because uh, dividing by 3 was the problem. Would have done this simple remainder, would have done this as well, simple remainder, would have done this as well, simple application of remainder. This I think was a challenging question, 2 steps for sure. Uh, again, 3 numbers to be looked at, but could have been taken a look at in the exam. Would have done this direct formula. I think this was also a challenging question, especially because of the option B, which had to be checked. So one of 6 and 8 could be looked at. Ninth, I would not have looked at in the exam. 10th, I would have. And therefore, 2, 4, 3, 7, 8, 10. Some of you might say, if not 8, better than 8, the question would be 6. So 2, 4, 3, 6, 7, 10 could also be the selection. But this would be my 6 questions for this test.